Okay. Hi, good afternoon or good morning or good evening, depending on where you are in the world. Welcome to the fifth, this is now session of the Spring 2026 SunoikisisDC Digital Classics program. This semester we're focusing on digital approaches to cultural heritage, and today's session is on GIS, Geographic Information Systems. And our presenters are Chiara Palladino, who you know from Durham University, who's been the co-organizer of the rest of this semester, and Becky Seifried from the University of Massachusetts Amherst, who, if you've watched previous years of SunoikisisDC, you'll also know as Becky normally presents GIS for us pretty much every year, and a first-time presenter, Cian Colgan from Furman University. They will all introduce themselves in a little bit more detail when it comes to them. Quick note just to people watching us live, please feel free to use the live chat feature to both say hi and introduce yourself, but also to ask questions or make comments at any time during the session, and we'll get to those at the end and we'll address them and answer any questions that are there. Greetings also to anyone who's watching us asynchronously after the event. Unfortunately, we can't take live questions from you, but we're delighted that you're watching nonetheless. Okay, I'll hand over to Chiara, who's going to introduce the session.
Well, hello, everybody. Welcome. Today, we're going to be talking about geographic information systems, particularly for cultural heritage. So as Gabi said, my name is Chiara Palladino. You know me at this point. So I'm here mostly in the capacity of researcher around geographic information systems for ancient sources and for the study of the past. And I'm actually delighted to have Cian here as one of my former students at Furman University to talk about a very specific research project that he worked on. So I will just be giving a very, very quick introduction around the usage of GIS for cultural heritage for our purposes. And then I'm going to hand it over to Becky for some fundamental concepts and keywords around GIS. And then after, I'm going to give you a very quick demo around QGIS, how to get started, how to load files, and so on. And then Cian is going to introduce the notion of least cost analysis with this tool. So what do we use GIS for in cultural heritage? Well, the answer is, as you can imagine, very nuanced and very long. We can use GIS for many things. Obviously, many of them pertain to spatial analysis. We can use GIS for landscape archaeology, for site discovery, but we can also use GIS as a tool for the management of data that have something spatial, some sort of spatial information to them. We can use it for crowdsourcing cultural heritage. We can use it to monitor cultural heritage sites. We can use it to analyze patterns around settlements, historical locations. We can use it to analyze documents, of course. We can use it to model large-scale circulation patterns, and so on and so forth. And typically, we use GIS in combination with other applications, with 3D models, with virtual reality, with predictive models, remote sensing, and so on and so forth, databases, and so on and so forth. So sometimes we can use GIS for site discovery. So basically, in combination with remote sensing techniques, we can use GIS to detect or to document the location of archaeological and historical sites. And also we can observe without actually being there and identify particular structures, their current status, their change over time, and so on and so forth. These kinds of tools are also particularly useful because they enable new forms of participation in crowdsourcing projects. We can use remote sensing and satellite imagery to collect information about the situation of a particular site, or even to involve the public in the detection of sites without requiring a very extensive amount of training. Potentially, we can use these tools to cover very, very large areas and very huge areas of land without needing to be physically there, or without need for extensive tools of landscape archaeology or landscape analysis. And this is particularly true nowadays, when we can use automation and machine learning tools to process very extensive amounts of data. We can also detect archaeological features beneath the surface. And this obviously has very important implications for archaeology and for the preservation of sites and the detection of sites. And then finally, of course, we can monitor the situation in cultural heritage sites, particularly in situations that are not easily reachable for various reasons, because they are in hostile environments like a desert or underwater, or because they are in war zones. So for instance, EAMENA, one of the most important projects in this sense, is a database that documents the change in time of sites at risk. And so we can use different satellite imageries and different images that were taken at different moments in times to document the current status or the past change of a particular archaeological site. We can also combine GIS with archives and with databases or with text analysis, as I'm going to show you in a minute. In one of our last sessions, collaborative geodata, we were shown this particular showcase, global approaches to early representations of the human figure by Professor Sebastian Eath, who connected mapping tools and location tools with a gallery of, particularly in our case, human figures or objects representing human figures from a variety of repositories. We can use GIS to model mobility at large scale. Many people may be familiar with projects like Orbis Stanford or Itinere, for instance, which use GIS and probabilistic models like agent-based modeling, for example, to model large-scale patterns of travel and connectivity, particularly in the Roman Empire. Itinere is probably the most recent example of the application of these methods to mobility and to connectivity with the Roman roads. And Itinere is particularly nice because it also combines 3D layers with custom itinerary calculation and with their connectivity models. So it's possible also to see how the terrain looks like from different perspectives. And then finally, and this is the project that Cian is going to cover more extensively, we can use GIS to model complex narratives of travel from ancient documents. And this is a methodology that we can combine with text annotation and with a variety of tools for spatial analysis. And we can discover new things and we can analyze spatially dense texts in new ways, trying to figure out what particular patterns of travel the text reveals, where the differences lie in the terrain and in the routes as we know them, and investigate ultimately what sort of new information travel narratives from the past can reveal to us. So a variety of methods and a variety of applications in many different fields. Before we dive into one of these particular use cases, however, we need to cover key terminologies and basic concepts. And for this particular overview, I'm going to leave the stage to Becky.
Thanks so much, Chiara. That was a really helpful way to frame the importance of GIS and geographic information systems more broadly. So now I get the fun job of explaining some of these basic concepts of GIS. This is the nitty-gritty crash course. Hopefully, if you have questions, drop them in the chat. This will prepare you for the demo that Cian's going to give us later. So first, a core concept of GIS is that GIS can act as layers. When we are using GIS in a software, all of our data is represented as different layers within that software. First of all, an important concept is that these data are essentially an abstraction of the real world. We are representing different things in the world as different layers in our GIS. Each kind of thing is usually represented as its own GIS layer. So in this example, we see here the real world on the bottom. We see a layer that's representing land usage. So we might have like areas that are designated as water, others as residential properties and things like that. We might have another layer that's representing the elevation or topography of the landscape. We might have other layers that are representing property like that are owned, maybe the streets, maybe the individual people. Another concept is that the layers at the top of this stack are rendered above the lower layers. So this operates a little bit like Photoshop or some other kind of imaging editing software. Another core concept is that GIS data also acts as a database. So we have two components to GIS data. The first is where it's located in space. So this might be as simple as a point location, which is a coordinate pair, an XY location in space. But in addition, if we look inside that GIS data set, we can see that there is a database that contains other kinds of information about that spatial location. So in the screenshot, we're seeing an attribute table. I'll talk about that in a minute. But that contains all kinds of other information like the file name, the number, admin name, and so on. All right, so this is where we can talk about the two different kinds of GIS data that exist. We have vectors and we have rasters. So first, core concept, both of them, great. We can use both vectors and rasters to represent the real world, and they do so in different ways. And so in this example here of a ski slope area, we could use points, lines, and polygons, which are all different kinds of vectors, to represent the cafes, the ski lifts, and the forested areas of this ski area. But we could also represent those same things as raster data. So there isn't a right or wrong answer. In the demo, we'll be using both kinds of data. They just represent the world in different ways. So this is an example of what vector data might look like. This is a real archaeological data set in the bottom right corner, which are survey units from an archaeological survey that was carried out in Cyprus. So each point in this map represents a unit that was surveyed by archaeologists walking through the fields. And associated with each point is a row of data in what we call the attribute table. So every point has its own row in this attribute table. And this is where we can see things like what is the unit ID, what is its location in space, how many artifacts were collected, and so on. There are other kinds of vector data. We also have lines and polygons. And together, those three things, points, lines, and polygons, are the different ways we can represent data as vectors. Rasters, on the other hand, represent the world as an array of pixels or cells. Each cell usually just has one value associated with it. So we can already see one of the limitations of rasters is we can't store a ton of data. We can't have many different attributes, just one attribute really. And in this case, what we're looking at is an elevation raster data set of the Grand Canyon in the United States. So we can see that the really dark purple in here are really deep areas of the canyon, and yellow are the high mountains and so on. And so in this case, if we queried each pixel or cell, we would find out that it would give us like the elevation above sea level for that particular pixel. One of the concepts between both of these data sets is that of resolution. Both vectors and rasters come in different resolutions, and this means basically how detailed is that data set? So in the bottom, we can see that a low resolution raster on the left with 8 meters is going to appear very pixelated to our human eye. As we drill down to a 1 meter resolution raster, that means each pixel is representing 1 meter on the Earth's surface. It's going to come into more focus. It's going to be a higher clarity image. The same is true of vectors. We can have very coarse, just a couple vertices in a line that represent kind of where that line is going, or we could be very detailed and capture lots of curves and things like that. And so this is just something to think about when you're working with GIS data is what is the resolution of it? Higher resolution can be great. It also is larger. Those file sizes can be much bigger. And so with rasters, we can move from a few megabytes easily to multiple gigabytes, depending on the resolution. Okay, so now we've learned about vectors versus rasters. Another core concept in the world of GIS is coordinate reference systems, which I'll just be referring to as CRSs from here on out. I like to ask this question before we dive into this topic, which is if I told you it was 40 degrees today, how would you dress to go outside? If you are from the United States, you're going to dress for cold weather because we use Fahrenheit here. If you're anywhere else in the world, you're going to assume it's very hot outside and you're going to bring a bottle of water with you. The reason I ask this question is it's the same deal with CRSs. I can give you a number and say where something is located in space, but if I don't tell you which unit or which system of measurement that number is from, you won't know how to interpret it. And the same is true with our geographic information systems. So there are two core kinds of coordinate systems. The first are geographic coordinate systems. The giveaway for you to know that that is the system that your data is using are that those numbers are represented as latitude and longitude values. If anybody has encountered a spherical globe on a desk or something and spun it around, you'll note that there are lines of latitude and longitude drawn on that three-dimensional globe. The equator is the 0-degree latitude line. Going up to the North Pole goes up to values up to 90 degrees, and the South Pole is negative 90 degrees. Similarly, lines of longitude go from 0 degrees to 180. So if your data has values between 0 to 90 or 0 to 180, you know that you're using a geographic coordinate system. And so I've put as an example, the coordinate location for where I am right now in Amherst, Massachusetts is 42 something degrees north and negative 72 degrees something west. The other family of coordinate systems are projected coordinate systems. Basically, these are using fancy mathematical techniques to take items or feature locations that are on a spherical surface and pretend they're on a flat surface, even though we are not actually on a flat surface. The Earth is not flat. This is always imperfect. We're always just trying to approximate three-dimensional world space as best as we can. But the real advantage of doing this is that we can now measure distance not in decimal degrees, which doesn't really make sense to a human brain, but we can represent distance in units like meters or feet or so on. And so here I've shown my location. It's that same location, but now showing it to you in a different coordinate system that is using a projected system. And so I'm 700,000 meters in some X space and 4.69 million meters somewhere along a y-axis. This means that if I told somebody, the distance from my town to the next town is so many kilometers, we could actually do that math on paper and then plot that location just by adding some number of meters to the X and Y. Coordinate systems, basically they can be converted between coordinate systems very easily. And so I can take my point where I am in Amherst represented as decimal degrees, and I can convert it to meters in a different projected coordinate system. GIS software is able to do this pretty seamlessly, usually without us even asking to do it. But it's important for us to know what's going on and that this is something that the GIS is doing for us. So a quick recap of these two things is that geographic coordinate systems represent the world in a three-dimensional space. They're best for 3D surfaces like a globe, and then projected coordinate systems we'll use when we really care about spatial accuracy and we need to know down to the centimeter, for example, that our location in space is accurate. One of the issues that comes up with using projected coordinate systems is that they always distort representation of real world. They're always going to be distort in either shape, distance, or area. And every projection system that exists, and there are thousands of them, they try to minimize one or more of these types of distortion. And so I'm just going to show you two examples to illustrate. We see here the Mercator projection. This is probably one of the most well-known. It's often used to represent world maps. So I've got a little screenshot here showing how Alaska and Brazil in the Mercator projection look like they are the same area. But if we use a tool like the truesize.com, we can grab one of these areas and we can drag it around the map. It's quite fun to play around with. And if we drag Alaska onto Brazil, we can see that Alaska is actually much smaller than Brazil in area. And so here we can see that the Mercator projection, it's preserving the shape of both of these states or countries, but it's distorting area, and it's also distorting distance. Another way to represent the distortion of projection systems is to use these different visualizations. There are links in the slides, so you can click on these and go explore them on your own. But particularly the left, that person's face is not supposed to look like that, but this is what happens with Mercator projection. And on the right, all of the circles are supposed to be the same size and distance from each other. We can see that they are all circles, so again, it's preserving shape, but it is really distorting area and distance. Another example of a projected coordinate system is the azimuthal equidistant projection. This is what's used on the UN logo. So I've got the logo there so you can see it. It's just centering the North Pole on the UN logo rather than the equator. But we can see here that the benefit of the azimuthal equidistant is it's preserving distance from the center of the map, but it is distorting shape. Those circles on the right are not all circular, and it's distorting areas. Some of them have more area than others. So you don't need to remember all of this, really, other than to know that projected coordinate systems give us some advantages, but there are also some things we need to be aware of. So once we get to the point, which is coming up next, where you are exploring GIS in QGIS software, there are two places in the software where CRSs matter and where you have an opportunity to find out more information. The first is that every data layer has its own CRS. So if you download the demo pack for this session and you investigate its coordinate system, you will find out that each spatial data layer has a predefined CRS. This is information that's encoded in the file itself. We can't change it without making a copy and doing some kind of like algorithmic projection of that data. The other area where CRSs matter is in the QGIS project itself. So this is something where we can basically tell QGIS, I want you to show me all this data in a CRS of my choosing, and it will do something called project on the fly, which basically means it will kind of temporarily distort that data to make sure it all is aligned properly. This is the magic of GIS software. This is what allows us to use different data sets with different coordinate systems in the same project. And so this slide, if you want to come back to it, will show you, explain to you how you can go about investigating those things. You can change the QGIS project CRS, you just can't change the data layers. Okay, the last topic that I get to talk about is how do we change the way our data looks in QGIS? So in GIS land, we call this symbology. Sometimes it's referred to as style. One of the fun and really great things about GIS visualization is that we can use any of the values that are stored in the vectors attribute table or in a raster's cells or pixels to change the way the data looks. We can do things like change the size, the color, the transparency, and we can also apply labels based on the information in these databases. So on the right, I have an example using a categorized or unique color scheme based on the state or province name for Canada and the United States. So we can see here, I've just applied a random color. I did not assign these colors myself. That would have taken a lot of time. Instead, I just said, hey, look at the attribute table, look at the names of all of these states and provinces, and please apply a random color. Another thing we can do is use numerical or measurement data. So here we have a field in the attribute table that contains the area in square kilometers of each of these states and provinces. And I've asked QGIS to use a graduated color scheme, which means going from one color to another to represent size. And so here we're using a darker color to represent smaller states and provinces and a lighter color to represent larger states and provinces. This gets into a lot of complexity because I, as the data visualizer, can go in and like refine those what we call bins. And so if you ever look at maps, this is called a chloropleth map, especially election data. This is notoriously where people can start to manipulate the way the map looks a little bit. Then now we're getting into cartography, so I'm going to pause there. But keep in mind, you can have lots of fun with this. This is another example of automatically applying labeling using a field in our attribute table, and also so we can see those labels showing up in the map. And also we've applied a light to dark color scheme to reflect population density of these different neighborhoods. And finally, raster symbology. So here's a great example of an elevation raster, which we're going to be using in the demo. Here we're applying a dark to light color scheme that reflects elevation. So elevations that are lower are darker, and elevations that are lighter are higher. All right, that is the portion of explaining the basics of GIS. So now I get to turn it back to Chiara, who's going to talk about getting started with QGIS.
All right. Okay, so this is not going to take very long, but in the hope that everybody has their own QGIS installed, and hopefully they're able to open it. And if you weren't able to download it, install it, and open it, there are instructions for this in the seminar page on GitHub, so make sure to follow them. I will show some slides on how to get started, and then hopefully I'm going to live demo a couple of the things that will be useful to follow Cian's exercise in a minute. So hopefully, again, you have downloaded and installed QGIS. We do recommend the long-term version. If you own a MacBook, chances are that you might be getting kind of a nasty pop-up the first time you open it. There are workarounds for that, so see GitHub for the instructions. And then finally, what you need to do is to create a new empty project. So all of this should be fairly straightforward and easy to do. The other thing that you will need to do is to install a couple of plugins. Plugins are very, very useful to introduce external material into your project and making sure that you have, for instance, an easy map layer to call when you need it, or multiple choices in terms of things that you want to add. So the way that you do that is you go to the menu, you click on plugins, and you click on manage and install plugins, making sure that you can open that. And there are two plugins that we recommend you have for this exercise. One is the Quick Map Services plugin, which you install directly in QGIS, and then the Least Cost Path plugin as well, which will be useful for the exercise. Quick Map Services is a quite useful tool to have different types of map layers in your QGIS project very quickly. If you have installed the plugin, you can call it through web. Again, in the menu, you click on Quick Map Services and you click on Search QMS. If you click on Search, you can search through many different types of maps. And for instance, the Esri satellite is a pretty good one for having an easy non-labeled satellite map in your project. The other option that you have, which we have provided in the GitHub instructions for the exercise, is pulling the map tile from the Ancient World Consortium of Mappers. And that is a different sort of beast. There are very detailed instructions on GitHub and on the link that we have provided to visualize that as well. Something else that you need to know in order to be able to follow Cian's exercise is how to open the processing toolbox, which is going to give you access to the cost distance analysis plugin. So you go to processing from the menu again, you open the toolbox, and this is an independent window that will be staying in your QGIS project for the time that you need it. You can minimize it, you can take it out from your project, but it will give you access to the cost distance analysis. So open the toolbox, scroll down to cost distance analysis, and this is what you will be needing to do the least cost path exercise. For the Ancient World Mapping Center map tile, you can follow these instructions again, and you have these details on GitHub as well. So I'm going to show you a couple of things of how a project would look like in QGIS itself, and spend maybe 5 minutes to show you a couple of key things that you need to make sure you have and you know in order to follow the exercise. So this is my QGIS project. And as you can see, I have downloaded a couple of things already, and I'm going to show you how to do that. And this is the essential overview of what the tool should look like for you as well. Hopefully you will have a nice map tile here, and hopefully you were able to access the processing toolbox, which should open as a section, a pop-up in your project here on the right. And here you can see the cost distance analysis as well. So there are a couple of things that I want to mention about the application as you see it. One very important part that you will be playing with all the time is the layers. And the layers panel is over here. Typically, you can, generally it's already open, but you can access it by clicking on View and switching it on from panels. You can see that mine is active. Here you will be able to see the layers and the files that you upload. Something else that you may want to do is to access the very, very useful attribute table that Becky mentioned in her explanation. The way that you do that is you right-click on any layer that you have previously uploaded and you click on attribute table over here. And you're going to be able to see what your dataset actually looks like. All of the attributes, the different latitudes and longitudes, the labels, everything that you have that might be useful to further manipulate and style your layers is going to be here. And you can keep this on or you can close it by clicking on the little X in the upper right corner. Some other things that are very useful to know, Becky mentioned that the possibility of styling the symbology of your layers in many different ways, and you can access this very easily by double-clicking on your layers and going down to symbology over here. You can change the way that your layer is displayed in QGIS in many different ways. Obviously, you can change the size, you can change the color, you can change the marker style, use different symbols, and so on. And these are all the sort of basic symbology options that you have. You can do a categorized view if you have values according to which you might want to display your data. You can do the graduated view if you have significant numerical values in your attribute table, and you can do a bunch of other fun things like create a heat map and calculate point displacement and so on and so forth. You can also display the labels with this other option in the menu, and you can decide what the labels are going to display for you, depending again on what you have in your attribute table. I'm not going to do that. I'm just going to click on cancel, but I wanted to make sure that people were able to navigate across all of these different things. And these options for styling are available for any type of layer. So you can have them for points layer, but you can also have them for raster layers like the clipped dem that we have here from Cian's exercise. How do you upload different layers? This is provided for you in the slides as well as screenshots, but I'm going to show you very quickly how to do that for what is relevant to the exercise that's going to come. So by the way, in the layers panel, you can decide to toggle your layers and to see them or not to see them, depending on what you want to do. You may also be able to change the overlay of those layers. So as you can see here, I can move my layers around to change the visibility, and this, in this case, just makes my point data invisible because it brings them backwards with respect to my layer. So as you can see, the points have disappeared, but you can change them back by changing, again, the display of the layers. You can also remove a layer from here. So you can also get rid of everything if you made a mistake, and so on and so forth. How do you upload a layer? You go to Layer up here, and you add a layer from this option. You have several different options. We're going to go through raster because this is relevant for the exercise of today. You can do the limited text layer if you have a table. You can do a vector if you have something like a GeoJSON file, and so on and so forth. There are many different options for you. So the raster layer is what we're going to need for our exercise and to upload the DM. So you click on raster, and you can select your raster data set by clicking on the three dots in here. This is going to open your usual browse option, and you can select your file from the folder for this exercise or any other folder where you have a raster that you wish to visualize in QGIS. It's as simple as that. You click on Add, and then you close this. And as you can see, my DM has appeared in my QGIS project. For point data, in our case, we're operating with shapefiles. So what we want to do is actually just drag them into QGIS without even thinking twice about it. So if you have your point data from Cian's exercise at hand, somewhere open in your local folders, you can simply take the shapefile, and the shapefile is the one that is named as SHP, and drag it in here. You're going to see, hopefully, that my file is being dragged, and this is the SHP file, and then release it. And as you can see, QGIS simply opens the file for me. And this is the magic of shapefiles, which are admittedly quite old-fashioned for many things, but they are definitely one of the easiest options to work with in QGIS. So this is pretty much it for layers and for manipulating layers in QGIS. I want to show you another couple of things just to make sure that everybody is on the same page. Becky mentioned the importance of the coordinate reference system, and you access that for QGIS for your project by using project and clicking on properties. As you can see, there's going to be a variety of options here for you. For the purposes of our exercise, the CRS that we are going to use is this one that you can see here, which is called the EPSG 32637 of the WGS 84. And there's an explicit reference to this in the instructions for the exercise. You can search for it by filtering it in here. So if you just select the numbers 32637, you're going to be able to see it. And if you've used it recently, you're also going to be able to see it here under recently used. You click on OK and make sure that your local projection is rendered correctly. You can also obviously zoom in and zoom out from your view. As you can see, this is my map tile here. And you can zoom in your specific selected layer by clicking on this very, very useful tool, Zoom to Layer. And you can go back to that very quickly. You can zoom in as well if you want a much more specific view of what you're doing with the obvious zoom in and zoom out tools. I think I've covered pretty much everything that is going to be useful for the exercise. So right now I'm going to shut up and let Cian present his project and the exercise, the tutorial for today.
Hello, everybody. Thank you, Chiara, and thank you, Rebecca, for both setting up both the technicalities of QGIS and some of the technical terminology of GIS in general. Both of those are going to be very helpful for what we're about to do today. So let me get started with the demonstration on these cost analysis in QGIS. But before that, it's probably important to actually know what we're demonstrating and what we're researching. So I am Cian Colgan. I've mentioned that. I'm an undergraduate student, 4th year at Furman University here in the US. And I've been working for the past almost 4 years now, on a project called Tracking the 10,000, which is a research of the Anabasis of Xenophon. The Anabasis of Xenophon is a military travelogue. It was written in 370 BCE, so about 2,500 years ago. And it recounts the so-called 10,000, who were a Greek mercenary army hired by this Persian prince named Cyrus the Younger in a failed coup against his brother named Artaxerxes II for rulership of the Persian Achaemenid Empire. The events that it recounts, written by Xenophon, who is a soldier in the army and rose to the rank of a commanding officer, took place in 401 to 400 BCE. And this is a very important text because it's the only surviving contemporary account of the expedition in its entirety. There are some other primary sources that have variable reliability or variable survivability. So this one is a very valuable resource for this specific event. And to look over the general route here It starts at Sardis, which is near modern Sart in Turkey, and it ends eventually at Bergama, and they take this very long circuitous route. So they go from Sart to the Battle of Cunaxa, which is a little bit left of Mahmoudiya in Iraq, and then up to the Greek, where Cyrus is killed, and then the Greek soldiers suddenly have to retreat back to the Greek mainland. So they go north to Trabzon, which is a Greek-speaking city on the Black Coast, then west to Byzantium, modern-day Istanbul, and then they campaign around and finally end the narrative at Bergama. So we're going to look at a specific problem. This comes from book 5. So here is that map over earlier that shows the entire route, and here is our specific area. It's this very tiny area in book 5, and we need to get from the city of Karasis to this city called Metropolis, which is what the Greeks do. And you can see from right here, even from the zoomed in location, it's a very mountainous region on the Black Sea coast. This is very rural, even today, a very rural area. So it can be difficult to navigate these valleys, especially when we're considering a large army that had horses, had a large baggage train, had carts, fleeing enemies, having to make deals with the local people who were living here that were sort of autonomous from both the Persians and the Greeks. So there's a lot of factors going in to inform our route here. And I am going to show now in QGIS how we actually do that. So here is the DEM and the point layer. Now I'm actually using what you would download online, the DEM. If you download the data from the exercise, it will be already clipped for you. But since we have the time, I would like to go through and show you how to clip a DEM very quickly, since it's very simple. And it also allows me to talk a little bit about the study area of our project. So what we're going to do is clip the DEM to a mask layer. So, oh, actually, before we do that, we need to talk about the CRS, the coordinate reference system, and our attribute tables. So you can see right here in the bottom right corner, we are in 32637, which is the coordinate reference system we are using here. But if we check data, it's always important when you're downloading data to make sure that's good. You can right click it, go to properties, and I wait for this window to pull up, and we go to source, and we can see it is projected in that same coordinate system. And take my word for it, all this stuff is projected in that same coordinate system. But if you were to download this stuff, again, these lime green are the visited points in the area, and then this purple spot is Metropolis. We just say that because it's ambiguous. We don't quite know where exactly it is. This is the best data we have, fetched from Pleiades, which is a gazetteer. So I happen to know where Karasis is because I've done this for a long time, but for you all, where might that be? So let's go to our visited locations and let's open our attribute table. And we can see right here in this field the name of what we're looking for. So if we right click it, or actually if we just click it and we go here to zoom to map, we can select this, zoom to the feature, and then it doesn't work, and that's all right. But it is, oh man, okay, here we go. I love it when QGIS doesn't work well and freezes up on me. That's all right. We're going to do this live. So I am going to swap back to, I'm going to wait for QGIS to buffer, and I'm going to swap back here. And I'm not going to show you how to clip it after all, or yes, I will. So we had right here this DEM layer. And what you do is you go to layer, create layer, and a new shapefile. And we're going to select a polygon shapefile. And what that will do, it will pull up on your mouse an area to select vertices for this polygon. So you can see I went around here and selected this is our study area. Eventually they end up at the city called Katiora, which is why this third point is labeled in our study area. So this is Karasis, Metropolis, Katiora. We need to get from here to boom to boom. So we go all around this study area, and we know since the text says Xenophon went from here to here, they probably didn't travel along the coast, which is why this is excluded. And it's also important when you're using a DEM you can set up barriers and things like that for least cost path, but least cost will try and map you through water features without previous guidance beforehand, since that registers as low elevation, flat terrain. So obviously it's going to think, wow, there's a big field here. Why wouldn't you go through that? So when we are clipping our DEM, we want to make sure we exclude the Black Sea coast, and I also excluded some major inlets here, so that it's just an easy way. There are multiple ways to set up barriers, but this is an easy one. And so when you draw all these vertices, you go to raster, extraction, clip by mask, and you select your input is the DEM you're starting with. The mask layer is your polygon that you just drew. And then you clip the raster by the extent of the mask layer. There's a checkbox to do that. And then you save the file. And boom, you have this clipped DEM. I'm going to go back here and see if this is working. Nope. All right. We are back. So now we're going to calculate the slope. So what we do is we go to raster, analysis, slope. And I'm going to, in the background, restart my QGIS while I'm just giving this talk. So what you would do is you go to raster, analysis, slope. Raster is in the top of your toolbar. Then there's a tool called analysis. Then there's the slope analysis. And what this does is we are working with, here we go, we are working with a DEM, which is a digital elevation model that has elevation values for different areas, which we are using, by the way. We're using the Shuttle Radar Topography mission, which is done by NASA. And it has a 30-meter, okay, this is cool. It has a 30-meter resolution. And so what this does is it calculates the slope from areas of high elevation to areas of low elevation and things like that. So this is just a slope tool. This is what is used for least cost path and least cost corridor, which we'll get to. So your input is the clip DEM that we just used, our study area. And we want to click express slope as percentages. This just works best for least cost path. It's just one of those things that's recommended to. And you save the file. And what you will be outputted is something that looks like this. Now, I have gone through and adjusted the symbology to look like something that I like to look at, because this is what makes sense to me. So the less slope, which is the flatter terrain, is these very light colors here. You can see where rivers are also accentuated in that light color. And the darker slope, or the darker color, is where there's a steeper slope and therefore harder to get up to. There are also ways, we're going to take a moment here to talk about how there are ways to complicate this process further in QGIS. For example, if you were to say you can only go up past, like right here, it will calculate it mostly linear according to linear process of increasing cost according to some of the baked in equations within the GIS software and within the system, within the processing tool itself. But if you wanted to alter that slightly and say, oh, I want, for instance, the computer to heavily penalize the cost of everything above, let's say, an 8% grade. So if the slope's above an 8%, I want to heavily penalize the cost, but I don't want to outright make it impossible for the computer to map through. And what that does is it will sometimes, for example, in a large study area like this, the computer might want to cut across a mountain, because that is technically the least cost path, despite being, for a person walking on the ground, very difficult, if not impossible to do. So what you can do is input some equations, and expression writing and equations are their own demonstration, their own thing, and probably their own class. But you can input some of those equations and alter how the computer interprets the cost of the slope. And that's very relevant for what we're doing next, which is least cost path. So let's say I just want to tell the computer, this is a very large distance, I want to tell it to get from here to here, from Carassus to Metropolis. There is a tool where it will draw a path on the least cost line for that. So you go to processing in your toolbar, then you go to the toolbox, which pulls up that processing pane that Chiara showed, and you go to cost distance analysis and least cost path. You can also, there is a search bar that you can search up least cost path. And when you open up the tool, okay, we will not be opening up the tool. When you can open up the tool, you can go to your cost raster layer, which is your slope. That's what is actually determining the cost of what you're doing. And then your cost raster band, for we just have a single band since it's DM, it's band 1. This is for other types of raster data, which can use color bands or things like that. That's much too far advanced and not relevant to what we're doing. So our start point layer is Carassus, and our endpoint layer is Metropolis. You go through the attribute table, you select both of those, and you input them in the start point layer and the endpoint layer, and there's a checkpoint to say use only the selected layer. And when you run this program, this is the output you get. I've overlaid it over the slope raster, and you can see it made a path that looks pretty reasonable. It goes around areas of high slope. it ends up at some point kind of going laterally up a mountain and onto the ridge line up top where it's going to be comparatively flatter, and then it moves around and meanders down back into the valley. So you might look at this and you say, oh, this is exactly what I want. And again, it is important when you're using these tools to understand that they are a model. Just as much as GIS is a model for the real world, that the raster data, for example, we have a 30-meter resolution. The real world obviously doesn't operate at a 30-meter resolution, and you can get very big features such as slopes, small streams, things like that, under that 30-meter value that won't be preserved through what we're using. We're using this because of size, and especially because it's publicly available. So you might look at this and say, oh, this is also a model of what we're doing. So this is not the path that they took just because the computer says so. Never say, oh, this is the path they took. Because what we would have to do is go through and measure this, make sure it actually measures for, in the analysis, Xenophon gives measurements, and for the scope of this project, we want to make sure that our real world measurements line up as best to our reckoning of what Xenophon's measurements mean to produce the most accurate result. And you can see here, it even goes through some of these river areas that I didn't exclude and didn't make a barrier for on the raster. So we might say, oh, we don't want that really, you know, this looks good at a first glance. Maybe it has some good stuff, for example, navigating through these valleys, but this is not our final output. So it's always important to evaluate what you're doing. Take a step back and say, does this answer our research question? So maybe what we want is, instead of one single line, one single feature, we would like a raster that shows a network of possible paths, the least cost corridors that we could take. So if there's a number of paths that go through an area or things like that. And so what we will do to start that is we will do a cost accumulation raster. There are a number of ways, since QGIS is open source and plugin reliant, there are a number of ways to calculate least cost corridor. It's not, but I will be using here a natively supported solution. So this uses the GRASS processing tools. So to access those, you go to the same processing toolbox, which was that panel on your right-hand screen that Chiara showed, and we used earlier. You go to GRASS, raster, R asterisk, and you go to R cost. You can also, again, just type in R cost, and you pull up this tool. That will pull up a panel with a number of inputs. Our most valuable inputs are our unit cost layer, which is our slope that we just said. Our starting coordinates. When you click that, it will pull up on your cursor a crosshair you can select on the map. You can also import coordinates, but you can select on the map the coordinates. I find that the easiest. I just zoom in on Carassus really close and I select that point. And since we have a 30-meter resolution, under 30 meters, it won't have too much of an impact on the actual routing through it. So we select Carassus, and our end chords would be Metropolis. There is also an optional thing that I used and that I recommend using in the exercise called use a knight's move. What that does is, if you think of a knight on a chess piece, the horse, it makes an L-shaped move. That just means that the computer will also factor in L-shaped moves rather than just vertical, horizontal, and diagonals. The reason why it's optional is because it takes a little bit more processing power. So depending on your system, you may not want that, or depending on your research area, your resolution, things like that, it may just not be necessary. But I selected it here in the spirit of going for the most accurate thing possible. And then we want to save all three of the output files. So the output files are the accumulated cost, a movement direction raster, and a cost allocation raster. And that will make 3 rasters. So what you can see right here is the movement direction raster, which looks sort of like this hillshade overlaying the cost accumulation raster, which has these colors on it. And what the movement direction raster does is it essentially calculates the cost of moving through a pixel in different directions. So to put that in a real world perspective, obviously it is a lot easier to hike downslope than upslope. If you are trying to trek up a mountain going straight up the slope, that is very difficult. If you're trying to trek up a mountain by going laterally and then switch backing across in a zigzag pattern, that is also easier. So this calculates in the directions of what you're doing. And then you're going to repeat this exact same process, but swap your starting coordinates and ending coordinates. So that creates what is called a back direction raster. So again, you are going to do the same process, but you will swap your starting coordinates. You'll make those Metropolis, and you'll make your ending coordinates Carassus. And what that does is it just accounts for all of the different directions. You have a forward direction and a back direction raster, and both of those are read by the processing program when you are calculating least costs. So if you are successful in all this, you should have 6 rasters, 3 that are for Carassus to Metropolis, and then 3 that are for Metropolis to Carassus. What I am showing here is the Carassus to Metropolis one. When you run the program itself, the Metropolis one is a lot bigger and takes up kind of this whole area because it's just calculating the least cost slopes that it takes to get to that location. So since we are trying to go from point A to point B, we need the cost of what it takes to get to Carassus from any point in our raster and what it takes to get to Metropolis. Because then what it will do is compare those two, combine those two, and compare those two to find least cost corridors through those combined. So next up, we need to make a corridor sum raster, which is simply combining those two. So what you're going to do is go to raster and raster calculator, which is in your top toolbar. And the raster calculator is an area where you can input these expressions. And so I have written one right here, a very simple one. This one combines the 2 rasters and finds the common ground between them. So you take your origin accumulation raster, which in our case, I named Carassus to Metropolis accumulation cost, and you add it to your destination accumulation raster, which in this case was the Metropolis to Carassus accumulation cost. And so what this does is it just simply adds those 2 and it finds the common ground between them. When you are doing this exercise on your own, this is noted in the exercise directions, and I noted here, you want to substitute the name of your raster in where I put these brackets, and you're going to want to remove the brackets. Otherwise, this will not work. There are also ways in QGIS, which I'm going to pull up one more time. There are also ways in QGIS to go straight through your excuse me, I lost my train of thought. Oh, to select feature layers in the expression panel, and it will just auto input the name. So it's very helpful. You can just auto input pluses, Boolean operators such as if, and, or not, and the names of your features and things like that when you're writing. So it's just quick and easy shorthand for that. So again, this creates, one more time, the accumulated cost rasters of both of those and the common ground they see. I adjusted the symbology again to show what I like the most. So it will not output like this when you run it yourself, and you are welcome and indeed encouraged to do so. Adjust the symbology for yourself so that it makes sense to you, so that you have an intuitive understanding of what you're looking at. So as you see right here, these dark red colors are the least cost, and these lighter and darker blue colors, as we get further away, are more cost. It's naturally going to take more cost to go all the way around here in this horseshoe formation rather than trying to take the most straight line that we can possible. Again, we can see the outlines of not just rivers, but valleys, and we can also see the outlines of ridge lines right here up at the top. And so what we have right now is we simply just have the cost accumulation. We don't actually have a least cost corridor yet. We just have the combined outputs of our cost rasters. To get a least cost corridor, we are going to again use the raster calculator and do one more thing. So we need to establish a percentile threshold. And what that means is that if we go back here, this is taking all of the raster pixels with all of the common value between our 2 inputs. We don't want all the pixels. This is not really relevant to us. We know they're not. We know they're not going through this way. So what we want is, let's say, the lowest 10%. Again, we want the lowest 10% of pixels, the lowest least cost pixels. So that is our percentile threshold. The actual percentage number will vary based on your study area, your study aims. 10% is just generally a good rule of thumb. So to get that, we will take the minimum value in our raster, the minimum pixel value, and we will multiply it by our desired percentage threshold. So for example, if I were to pull up you can find your minimum value in the properties. If you were to right click your raster feature and go to properties, you can find the minimum value. You can also find it in your symbology when you are adjusting the symbology feature. So for example, my minimum value for that, and should be the same on the exercise, was 16137.36. That was our minimum value. And so for me to get the 10% threshold, you multiply it by 1.10. If you were to do a 5% threshold, you would do a 1.05, multiply it, and you get this value. So hold on to this number. We go to our raster calculator, and we enter this expression. If our combined cost raster, which was our raster from the previous slide, is less than or equal to this value, we are going to make that 0 over 0 or undefined or no value. And so the reason why this formula is written in this way is because no value features in QGIS auto default to transparent. So it will just exclude it from visibility from our output. If your settings are different, there are advanced ways to change that. This will not work, and indeed you will have to go through a different sort of workflow for that. But there are many, again, just as there were to combine the cost values, there are many different ways to go through this least cost corridor. There are some plugins that can handle it, but they require a little bit of finicky setup. And for this demonstration, I just wanted to show natively supported solutions. So again, you would go to raster in your toolbar, pull up raster calculator, just as you did with the previous step. You will enter in this expression. You can just copy paste it here. Again, change these values and delete these brackets to be your feature names and your value if it is different. And then you run it. And what it should do is output something like this. Again, I have adjusted the symbology to be what I want. So these bright red areas are the optimal least cost areas. But you can also see these brighter yellow areas, which blend in a little bit to the base map. These brighter yellow areas, these blue areas are also equally least cost. So they are areas where perhaps, for example, let's say since this is a river, let's say, oh, it's too steep here. I don't think that they could reasonably track a shoreline there, but there's another river. Oh, well then maybe instead, assuming that the terrain was mostly the same and the water levels were mostly the same and everything, which is not a given for 2,500 years ago, but we'll get into that in a second, is let's say, oh, maybe this was a bit easier. So actually, perhaps they went down here and then tracked along this shoreline or up this ridge line or around this area. And so this just gives a better, or for our case, a more broad, not necessarily better. Better, again, depends on your project goals. But this gives a broad overview of some of the pathways through this area, the least cost pixels that the computer does. Now, again, to zoom out real quick, we're going to evaluate again. This was a very simple demonstration. Like I said, there are ways to factor in like critical slope thresholds. So for example, not pathing over a certain slope or heavily penalizing a certain slope via, let's say, a quadratic function. There are ways to say, oh, if you're running a different project, for example, oh, they need to be away from water. They need to be X number of meters away from water. There are ways to buffer water features. There are very, very advanced ways. This is just a very basic workflow. And the reason why we want this basic workflow for this project is because we are not taking what the computer says as gospel. We are not going through here and saying, this is our output, this is the most likely path that they took. We want to use this as a reference. We want to say, hey, this area is very tedious to manually go through with all these valleys to try and go through, let's say, Google Earth. You can street view, or you can what's called surface level layering, which just pulls up kind of the 3D model of the DEM that underlies Google Earth. And it just allows you to, it's when you go into Street View, but there's nothing to Street View, and it's just that kind of flat area. It still allows you to get a sense of what it's like on the ground, which is a very helpful thing to do. So for here, it's saying, oh, since that would be extremely tedious, it would be extremely tedious to go through here and manually put in, just as an exploratory option, manually put in all our vertices. And since we don't have the option of actually flying here and hiking this area, this is a way to say, okay, the computer freshly inputs these as our cost, or these as our least cost areas. These are some of the most likely paths one could take if, based on our very basic parameters, we are trying to get from point A, Carasis, to point B, Metropolis. Now, your job as the researcher is to go through and say, is that reasonable? Does that answer our question? In the best case scenario, great, this is a very reasonable path, in which case we can go through and hand measure it ourselves, or just, if it really worked out well, use the least cost path. But in other cases, we'll find out, no, this doesn't work. So for this specific project, for what I was working on, I did all of this workflow, and then I went back through and I measured this area, and it was way short of what Xenophon said it should take in the distance. And now that is a very odd thing to say. Normally you would say, oh, it's too long, and they took a different way. Too short is interesting, because you would ask, why did they take a longer route if a shorter route was available? And this is where you start thinking as a researcher, perhaps did they know of it, which is a hard thing to account for. maybe the routes were different, or the terrain was different in this area. Since this is a very mountainous region with a lot of river valleys, those don't tend to shift a whole lot over 2,500 years. Like very steep river valleys, you won't get a whole lot of stream avulsion that will massively change the topography. So perhaps a large scale changes to the terrain, or rather, I should say, perhaps the terrain looked very similar back then as it does today. Again, this is a very rural area even today, not super developed. So we look at the text, and maybe you read the context of the text a bit closely, where it says, oh, the Greeks marching this area encountered what they call a hostile tribe of the Masinoicians, which are just these kind of indigenous groups around here. And they encountered two of these peoples whom they lumped together, despite obviously not being in their own mind similar, because they're warring with each other. So they encounter a hostile group of the Masinoicians and a friendly group of the Masinoicians, and they say, oh, well, we need supplies, and we need safe passage through to get from further down the coast off this map. Will you, they go to this friendly tribe and they say, will you help us? In exchange, we will act as an army for you to help you win this war that you are in. So in reading that context, you will look at this map and say, maybe they didn't take the least cost path because they had external political reasons, external diplomatic reasons, external military reasons. Maybe they needed supplies, maybe they needed to hit certain strongholds, things like that. And so that's where it's very easy to or not very easy, I should say, but that's where you need to look at all your surrounding data, archaeological sites, anything that you can think of to help contextualize. Because again, what we are doing, at least in this project, what I was doing, is making a reconstruction. We are not saying this is the path that they took, this is definitely it because we ran, these quantitative analyses and things like that. No, we ran these quantitative analyses to inform our reading of the text. And by using these two reference materials together, we make our most likely outcome. So that was the demonstration. Thank you very much.
Great, thank you. That was very exciting. Very cool. Does anyone else have anything to add or ask? We'll keep an eye on the chat if anyone wants to send any questions in there. But in the meantime, anything anyone else wants to add?
Live demos are always so hard.
Yeah, I would have liked to actually demonstrate instead of working on slides, and it worked when we rehearsed this 5 minutes before start. But that's okay. That's okay. That's why we make these, and that's why we have the backups.
Yeah, that's yeah, and well done for having that backup in the slides. It was seamless. So yeah, brilliant.
While we're waiting for questions, I'll just say, least cost analysis has been kind of my specialty in the GIS world. And Cian, I thought you did an amazing job explaining both the utility for these kinds of humanities-based researchers and also the caveats, like the things we need to be aware of. Because the danger is really how easy it is to run these tools. You showed a rather complex workflow, but there are a lot of tools. You can just run a tool and GIS software will output something. And it's really easy to fall into the trap of thinking, oh, this must be the way it is. When in reality, if you change one little parameter, you'll get a completely different output. If you used a different resolution DEM, for example, you might have gotten a different corridor produced, or at least you might not have seen some of the cool alternate ways that somebody could have gone. So thank you for that really great explanation.
I was going to ask a question actually about Cian. You mentioned the rivers being potentially an issue with traveling through there, but that the rivers weren't reflected except as being low points on the map, and they weren't reflected in the least cost path algorithm or corridor algorithm. Is there any way that you could put the rivers in somehow and say, make rivers no-go areas or something like that? Is that
yes, of course,
is that something that you could have done?
Yeah, so there are a lot of different ways to do this. Many different ways, and it also depends obviously on what GIS program you're using, what kind of plugins you've got. So for example, one way is if you can download data of the rivers as a feature file, let's say a polyline, you can just say, oh, when you're doing this, this is a barrier. So if you are trying to traverse this polyline feature, it's a barrier. You can't do that. That has its benefits, and it also has its drawbacks. If you can find river data, that is awesome. If you are working in a very rural part of what is modern-day Turkey that has a little bit of messy government files or no files at all, and if they are there, they're in Turkish, which I don't happen to speak Turkish, that becomes a lot harder. Or even if you do input them, let's say they're not a complete stream network, and you don't want to go through and manually map it out yourself. That can be a bit of a challenge. So there are other, and also one more thing is you might not want to say, even let's say it is a complete network. Let's say best case scenario, you found this wonderful hydrographic data. An army could still get through a river. It depends on how deep it is. It depends on if there are fording points. It depends on how high it was in the season, which again, since we're working with the text 2,500 years ago, we have messy, we have rather ambiguous things on the specific chronology, the specific water levels. There are ways to, and there has been some excellent work done to say, oh, this was happening at around spring turned to summer time period. So they would have been decently high at this point with the snow melt in these more mountainous regions. So that would have impacted fording locations, fording distances. We also know, Xenophon mentions in the text, that there were roads and routes through this area. So whether those included bridges, whether those just included areas that were so commonly forded that it was easy enough to do so, is also up for debate. So it's very difficult to, again, use the program to just do that. Or to just kind of one size fits all it. There are also other ways, for example, in a raster calculator expression to say, and again, I didn't want to do this because it's a little more complicated. So when I clipped my study area layer, I just went around the coast. I just didn't feel like doing it. But there are ways to write in to say if it's under this certain slope, or if it's completely fat, or if it's no value, which is often what water features will show up as. Not rivers as much, because they can have weird stream banks, and the satellite and remote sensing tools used to do this can penetrate the water to a certain distance. But for big oceans like that, they will say no value, and so coastlines and things. And you can just say, oh, if it runs up as no value, don't map through it, no matter what. And there are many different ways to do that. I'm sure there are many more that I know of and am not mentioning, and don't know of and don't mention. But yeah, so there are definite ways to do that. They depend on the goals of your project, your familiarity with the system and the workflow, and oftentimes just the size of your study area. How tedious is it to do those things?
I'll also add, because I think a paper that I wrote with Chelsea Gardner on mapping the Lee Furmer's journey was a least cost-based paper, and I think it was one of the required readings for this session for the students who are taking this. Something we also did is we knew the locations of some of the pre-modern roads, and so we factored that in when we were making the cost raster and said that if there was a road here, then those pixel cells cost less than everything else. Like a casual way to describe that is burning it into the raster, but essentially we're just saying that those raster pixels cost less. And so I could see how you might do that with this case study with known locations of Roman roads, or if you're working in the ancient past, we know where some of those road fragments are. We also have researchers who've proposed like where there might have been roads, so one could take those locations and say those would be least costly, and that would help the algorithm kind of follow those paths better.
I guess that potentially could be circular, couldn't it? If they proposed it because they think this is the way they must have gone. But yeah, I mean, all of these things, as you say, if you're putting values on them to make it slightly easier rather than making them certainties, that would all be good.
You will all be pleased to know that my QGIS has finally started to work again after the demonstration. So I will simply pull up that in this presentation here, so we have something nice to look at.
Cian, can I ask you a question?
Yeah,
because Chiara showed 2 potential web platforms that one could use to find paths in the ancient past. So one of them was Orbis and the other was itinerary.org. Did you try those out, and why? What does running it in QGIS give you that maybe those web platforms don't?
So I have looked at those platforms. I use them again as references, much as these outputs are references. They are helpful. A lot of them are run. If they're run just on probabilistic measures, again, it will output the same caveats that we will do if we run it in QGIS, and the same nitpicky things. The reason why I run this in QGIS is because the specific text I'm working with is so dang odd. There are just weird measurements can be especially difficult, especially in these areas. They can be non-existent. They can go through, let's say, he just says, oh, well, we went a day's travel. Well, what's a day's travel? That's very variable depending on where you happen to be that day. What mode of transportation you're using? Are you on foot? How much luggage are you carrying? Are you on horse? All this stuff. Are you being chased? So I do everything I actually worked in ArcGIS Pro, but I do everything in the native GIS software, since it's a lot easier for me to manipulate and run and rerun something. When I am looking at, let's say, Orbis or something like that will have these outputs, at some point it'll only give me one, or in best case scenario, a very limited number of outputs. But here I can constantly change parameters, alter things, say, oh, I did that wrong, or oh, I didn't consider this, rerun the process, and make it very iterative. So it takes a lot longer, obviously, but it gets you a lot more richness and depth to the project. And again, I went through on that, where is it? On this map, this big one. I went through and did a similar workflow that I just showed you for all of these points. And it takes quite a long time. Some of it was not that involved, some of it was more involved. It depends, on the area that you're in, and it depends again on what previous scholars have said and things like that. So it's all representational. But I do this stuff natively. I recommend everyone else at least attempt it natively, because it's a lot more customizable, and no one's going to be working usually with the same exact research question, with the same exact text, with the same exact problems. So being able to do it yourself is a very good skill to have, especially when you know what you're looking at. That's why those foundational GIS techniques that you talked about are extremely important, to know what am I actually looking at, because I will output something. For example, if I just output this combined cost raster, I would say, oh yeah, that looks pretty reasonable. That's our least cost corridor, despite the fact that, like, well, why is it measured out here? Why do we need all this? This isn't really least cost at all. This just shows almost like a heat map of cost, which is helpful in its own right, but not quite what we're looking for. So we want something perhaps more like this.
I also want to mention, for the benefit of the people watching, since we talked about, these pre-existing or pre-made tools like Orbis and Itinerary and so on, which are fantastic on their own, it's also very, very important to remember what these tools were made for. As Cian said, it's very important to think about your research question. Orbis is a purely probabilistic tool based on data from the 2nd century Roman Empire. So it's very likely that it's going to give you interesting results if you're working within that area and within that chronological span. But people tend to use Orbis as a sort of catch-all type of tool, where in fact it's very, very specific, and the creators have been very specific in terms of what were the research questions that they wanted to answer, that were, again, around connectivity and travel in the 2nd century Roman Empire. And Itinerary is a bit more generalizable for many reasons, but it also is intended to be a model of land and specifically road connectivity in the Roman Empire that's based on a variety of sources. Part of them are primary sources, part of them are interpretations and re-elaborations of those sources. So again, it would be the same if anybody wanted to use Cian's project to map, I don't know, a medieval itinerary using data that is largely from, the 4th century BCE Xenophon route. So it's very, very important to make sure that we understand what these tools were made for and what we can use them for.
Are tools like Orbis and Itinerary using very different methods than GIS? Are they also using least cost methods? Or when you say they're probabilistic, does does that mean that they're actually not using GIS, they're shortcutting that somehow?
Orbis uses GIS and least cost, but of course it's more large scale than what we've been showing. So I think there's a fair amount of statistical modeling in there as well. And itinerary, to my knowledge, is a bit different in the sense that the single, the data points, but also the single stretches of each itinerary were verified at least manually. There is a small route finder in itinerary that you can use that pretty much is, I think, a least cost type of calculator that works within their data. So it shows you the most likely route that you can take across 2 points. But the functionality of that is not meant to replace Orbis. It's meant to help you navigate in their data set. The value of itinerary is in the sort of networked connectivity aspect and in the fact that they've been able to reconstruct and still are reconstructing a lot of that network.
Thank you. Yeah. Well, if there are no other questions online, I'm not seeing anything in the chat. Does anyone have any last words to say? We can wind up. In which case, just thanks very much again to all three presenters, and especially Cian for taking the risk of doing a live demo and for handling it so well when technical issues arose. If you hadn't kept saying throughout it that something would fail, we wouldn't even have known that you hadn't always been planning to use the slides. So it was great. Very well done. And so just a reminder that there's no session next week, but the next session that we have is in 2 weeks' time, then on Thursday, the 26th of February, and it's going to be on working with Indigenous heritage. So please join us for that if you can. Thank you all again very much.
Thank you.
Thank you all.